Ngalakin Khadijan Nyunga Boja.
Okay, video 33, final video. I'm going to talk a little bit about MongoDB. It's really part of a sort of broader suite of tools that goes under the name NoSQL. The term NoSQL, some people say that it stands for not SQL or non-SQL, and other people say it stands for not only SQL. Basically, it's used to describe a range of database management systems that are not based on the relational model of data. Now, it may have occurred to you that we've spent almost all our time discussing relational databases and all of the intricacies of the relational model, despite the fact that the relational model is, well, basically 50 years old. So one reason that the relational model has lasted for so long is because it is so staggeringly successful. But of course, it's not the only way to do things. And there's a range of other tools available. None of them have really sort of hit the big time, except perhaps for MongoDB, which is a type of database known as a document database. Now, what I want to do in this video is just talk briefly about what is a document database and how it differs from a relational database. Now, if you read web pages about NoSQL or something, then you'll notice that they have a fairly evangelical fervor with which they sort of describe SQL as being, you know, hopelessly outdated and difficult to use and so on, and they present their own database model as the sort of the way of the future. But I don't think it's useful to think of them as competitors. It's more useful to think of them as complementary, so that you use SQL when your data fits the relational model, and you use something else when your data doesn't fit the relational model. There's no point in deciding in advance you're only going to use this tool and then discovering that your data is not really suited to it. Okay, so let's look at the hype then. So NoSQL is often hyped as being modern and flexible and scalable, and usually they throw in a few additional keywords as well, like massive data sets, rapidly changing, and then cloud-based, because of course if something's cloud-based, then that's much more fun than it being disk-based. And they'll describe SQL as being a legacy system that's difficult to use, inflexible, does not scale out well. So in other words, NoSQL, or in fact any NoSQL really, is portrayed as a sort of disruptor, the cool creative disruptor, and SQL is portrayed as being sort of fossilized and stuffy and old-fashioned. Well, I mean, of course, part of those things are true, because SQL is fairly inflexible. It is not all that easy to use, and it doesn't scale out well. But that doesn't necessarily mean that all those other things are true. So the main difference then is whether to view data as being highly structured or loosely structured. So in SQL, the relational model, basically, we're forced to store our data in tables, and tables have rows and columns, and in each row or column, there's usually a single value. Though I should note that modern sort of extensions to SQL are allowing more complex data to be placed into the sort of the values, into the cells of the table. But for the time being, we'll just view data as being, in a relational model, data is always structured into tables. If new data turns up, then you have to fit it into the existing structure. If you happen to design a table and you're storing, I don't know, books or something like that, and you have a column for genre, then if you suddenly decide you want to store 2 genres for each book, not every book is just a single genre, well, then you have no choice really but to add another column, the second genre, genre 2, and that second column then has to be present for every row of the table, even if it just contains null. In MongoDB, data is largely unstructured, and basically new data of any type can be added anywhere at any time. So we're talking about lots of structure, not much structure. And the basic thing to remember is that if you're lucky enough that your data is highly structured, well, then it's a natural fit for a relational database. If your data is unstructured, well, then you have to get around that somehow by either using something like MongoDB or sort of jumping through hoops like we've done before to add additional tables to sort of accommodate data that's perhaps multi-valued, things of that nature. So I should just be careful here when I say I'm using MongoDB as sort of a representative for all NoSQL databases, but what I'm saying really is just for MongoDB, or maybe for document databases in general, but there are other styles of database as well, but I'm just going to be a little hazy with my terminology and confess that I'm really just talking about MongoDB here. Okay, what's the problem? Well, in a relational database management system, you have to decide on your tables, you have to declare your columns, you have to create the schema to create the tables with the right number of columns, the right type, and all the rest. The schema is designed in advance of any data arriving, and changing the schema is difficult. You have to use sort of alter table commands and actually make many changes to many rows just to make a minor change to the schema. The database is then normalized, as we saw in video 32, and that will minimize redundancy and minimizes storage requirements as well. Okay, so it's very much a plan in advance, then make the data fit into those plans, and then you get a system which is theoretically very solid, and the query optimizer can do things very fast because it can mathematically provably correctly replace queries with optimized queries. However, the data about a single entity, i.e. one particular student, may end up split over a large number of tables. So extracting the data, which is often, probably the main thing you want to do in a university database, is find out information on a per student basis. If the information for students is split over many tables, then you have to write a SQL statement that involves multi-table joins. Those statements are difficult to write, they're difficult to understand, and they can be time-consuming to execute if there's lots and lots of tables that have to be joined together. Okay, this trade-off was worth it in the 1970s because disk storage was very expensive. Nowadays, disk storage is much, much cheaper. Well, of course, disk and processing power have improved dramatically over the last few decades, but the relative performance of the relative cost of disk storage is way less than it used to be. So that means it's not so bad nowadays to store data twice, for example. It's not the overwhelming goal of the database designer is not to minimize the amount of disk space consumed. So as time has passed, trade-offs, the sweet spot of the trade-off has altered. Okay, MongoDB, like most document databases, stores what are called documents in a special key value format, which is normally called JSON or JavaScript Object Notation. So this object described above is what's called a document, and a document is loosely comparable to a row in a relational database. So you can imagine a table in a relational database storing all the information about a student. Then you can imagine this document as storing all the information about a student. Okay, so the document starts and ends with these braces, curly braces, and that tells you where the document starts and where it ends. Now, inside the curly braces, you can have any number of fields. Now, in a relational database, each row must have the same number of columns, though we can sort of get around that by using nulls. Each row then, or each entry, each field in this document, so that's one field, id:1, consists of a key and a value. So the key is sort of like the name of a variable, and the value is the value of that variable. So id:1, so colon is not part of the name, it's just separating the key from the value. So this document refers to an object whose id field is equal to 1. The name field is equal to Amy. Now we see something new. The addresses field, well, this now contains an array, not a single value, not a single string or anything like that, but actually an array which contains multiple things. Okay, so this is the opening brace of the array. This is the closing brace of the array. What are the elements of this array? Well, this array contains two things, and each of those things are themselves documents. So this is a document that contains an address. Well, sort of a pretend address. And this document's got two fields, add, address, and then a value, 3 Wallaby Road, and then postcode, 3002. So that means that the values, the fields in a document can be other documents, and so on. Okay, unit marks. Now I've got an array here, and I'm storing all of the unit marks for Amy, and each individual unit mark is a document that indicates a unit name, and a mark. And in this case, it's an array of two sort of marks documents because Amy has taken 2 units so far. So there you have it. We have keys, which are like variable names, and then we have values. And values can either be scalar values like 1 or Amy, or they can be addresses, or they can be arrays like the addresses 1. The elements of the array are themselves documents. Those documents in turn can themselves contain other documents, and so on and so forth. The point is, everything about Amy is in this one document. So Amy's entire record is here. No joining with like enrolled to find out the marks, no joining with enrolled and unit to find out which marks belong to which unit, and so on. You can already see that this is fairly verbose because we're sort of essentially we're repeating the name of the variables. We're repeating the names of the columns every time for every individual document / object. Okay, so each document consists of fields, any number of fields. Each field consists of a key, though not a key as in the primary key, foreign key sort of key, but just as in the sort of general computer science notion of a key value pair being the name of a variable and the value of the variable. The value can be a single value or an array, and the elements of the array can themselves be documents or single values or whatever. And so ultimately, we end up with a deeply nested structure where any information about Amy, no matter how different it is to the previously stored information about Amy, can simply be added to this one document. So it's basically like you've got like a bin called Amy, and everything you find out about Amy, you store in that bin or in that filing cabinet. So a document can be arbitrarily complicated. It can be nested to any depth. In a document database, though, all of the information about an entity is stored in one document. The sort of idea of documents within arrays of documents sort of brings to mind a sort of fractal structure. And so you can see that this is actually a type of broccoli, and that's got sort of little buds. And if you look at the little buds, then they themselves have got lots of little buds, and the little buds on the little buds have got more little buds, and so on. So that's what it's like for a document database. So just some terminology. In MongoDB, a database contains collections. A collection contains documents, and documents contain key value pairs. The whole system of a document database is set up so that everything is heavily indexed, and there are very fast search algorithms, which means that if you want to extract something from a document database, this is very fast. So the correspondence then between a document and a relational database is just that, well, a database and a database are the same thing. A collection, so that's a set of related documents, is the same as a table. So we might have a collection of student documents, and we might have a student table. Inside the collection, there are many documents, and inside a table, there are many rows. And roughly speaking, each document is loosely corresponds to a row in a relational database. Though, of course, a document is a much richer structure because it's got these, these subdocuments and arrays and all the rest of it. Okay, let's just briefly consider a sort of a relational versus a non-relational or a document approach in a sort of familiar context. Okay, you're probably familiar with the Internet Movie Database, imdb.com. You can go and look up, who was in all various movies, and there's ratings, people rate the movies, and so on. So the IMDb's got a huge database, and it makes that database freely available, and you can go and inspect it at this URL. That describes it, and that leads you to some links that will give you the actual databases. The databases are stored in tab-separated value files, so they're basically Excel spreadsheet style files, which is basically a sort of a relational structure. So title.basics stores information about the movies. Name.basics stores information about people. When I say people, I mean movie stars, directors, actors, actresses, and so on. And then the relationship between people and movies is called title.principals. Principal means the principal participants, the main people who are in this movie, and it's stored as a relationship between people and movies. Okay, so do I have space here? Yes, I do. So it's sort of like movie. Well, I'll use the same names to make it easier. So it's sort of like title. That stores all the movie titles. Here's an example of one of the things stored in that table. I've removed a few fields, but this is basically what it looks like. Okay, so what it stores is, well, it stores a key, which is just a code, an artificial ID that indicates a particular movie. This is the movie Jurassic Park that I'm talking about. So it says that it's a movie. That's a second field. It's because IMDb includes TV shows and shorts and cartoons and all sorts of things. It has a title, which is Jurassic Park, a date, and then it has a genre, except that this is sort of a sort of pseudo genre field because it's just glued together. It's just a text string containing action, adventure, sci-fi. So this database, as it stands, is not even in first normal form because we don't even have the property that each value is a scalar value. But that doesn't matter too much. Okay, then we have name, yes, names. Okay, so titles, well, we've got the code, the ID, and we've got the type, and the title, the actual name, and the year, and the genre, which is really a multi-valued attribute, but I'm not going to get into that now. And there are some other things which I've removed just to make it simpler. The names then contains, well, it contains a name ID, like a code for any particular actor, and then their actual name, and then their date of birth, and some other stuff which I have omitted. So these are sort of things in the name table. So Sam Neill, born 1947, he is actor NM000554. That's, if you look throughout the database, the IMDb database, that's how Sam Neill is referred to whenever he is referred to. Okay, and now we have the principles, and the principles has been implemented, or if you look at it, we can see, well, here's the name of the code of a movie. Here's the code of a person. And here's, well, what's that? Composer. I'll tell you what that is in a second. So that tells us, these two foreign keys tells me that principles is really relating a title and a name. The relationship attribute is the role that name played in that movie. So in the movie CITS1402, the person with name NM002354 was the composer of the music for this movie. The ones I've pulled out at the moment are just the actors and the actresses. And so here are the 4 actors and actresses. And if we look at those, if we look up those particular names in the names table, we see that Sam Neill, Laura Dern, Jeff Goldblum, and Richard Attenborough were the principal actors in that movie. Okay, so this is a relational style structure. Everyone who is in the movie gets an extra row in the principals table. So for each individual, we have the name. for each particular person who plays a role in the movie, we have one additional row of the principals table. Okay, it's sort of obvious that any title is going to have many actors, maybe at least one, I don't know. Well, I must have at least one, so let me put one to many there as the constraint, and let me put one to many here, because 0 to many there. Each name could be in no titles or maybe many titles. But anyway, the point here is that this is a relational structure. The three tables, title, the principals, and the names, are the ones that contain jointly all of the information about these movies. But in order to find out anything sort of sensible about any of the movies, you really have to join all of the tables back together. Okay, let's have a look at a similar thing. It's not exactly the IMDb thing, but it's a similar one in MongoDB. If you go to MongoDB website, you can sort of sign up for a trial account, and there's some sample data that you can play with. One of them is a database of movies, and what I've done is I've typed this in, and that's a sort of says that I want all of the documents in this collection that have title field equal to Jurassic Park. Okay, you can ask for, you can ask for things like year of release was 2000 or anything. You can use, there are many, you can use operators in these queries just as you can in SQL. Okay, so let's see what this object looks like. Well, first of all, it's got a sort of internal ID, _ID. That's essentially a hash code of what information is contained in it. These are all the keys. So year 1993, plot. So plot is a string, and a string is like, and this string is the description of the plot. Now look at this one, genres. Now it's stored an array. Okay. Well, this is a document database, so your values can be arrays, and so now it doesn't matter whether you have one genre or 3 genres or 10 genres, you can just use an array containing as many genres as you like. It's got a rating, a title. There's the title Jurassic Park. That's what I asked for, so that's obviously what I'm going to get. And then it has, well, here's the cast. That's an array. The directors is an array. In this case, there's only one director, so the array only has one element. But I think you can sort of get the idea that all of the information about this movie is sort of in this single document. Okay, well, let's see if we can dig deeper. So let's see if we can find out who the cast actually were. Well, that means we need to look at the elements of the array, and in the sort of graphical interface supplied by MongoDB, you just have to click this little arrow and it will sort of open that array. And now the array's open, and we can see that here is the cast. Sam Neill, Laura Dern, Jeff Goldblum, Richard Attenborough. Okay, much more natural than the SQL way, but also in some ways more limited than the SQL way. Because like we can't go any further now with Sam Neill, we can't, we can't find any additional information about him. If this was sort of a fully fledged document database, then instead of just the string Sam Neill here, we might have an entire object representing Sam Neill, and that would be name, date of birth, date of death, and so on and so forth. But then that would be repeated in every movie that he was listed in. Okay, so there's really two sorts of things. How organized do you need your data to be? How do you personally organize your own stuff, like your digital photos? Okay, some people are very organized. They have a folder for each year that they took the photo. 2018, 2019, 2020. Within each year folder, they created subject folders, family, work, school, and so on and so forth. A super organized hierarchical organization where every photo has a precise place. Alternatively, you could do it differently. You could just have, well, just a giant bucket that contains all of your, well, photos, contains all of your photos, okay? But then maybe you could use like tags, for example. As you take the photos, you apply some tags to them, you know, family, work, friends, so on, or the data that's already included inside each photo file, like which includes the date and the location and that sort of thing. So organization is the hierarchical, very careful, blah, 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 and is replaced instead by search. So instead of organizing things so you know where everything is, you just label everything so you can find it. I mean, really, this is sort of, I think Google has sort of shown us that search can really replace a heck of a lot of organization. You don't really need to have your files super organized in your file system because it's very quick to just search for whatever you want. On the other hand, if your data is naturally hierarchical, well then it makes sense to store it in a hierarchical structure. Okay, one phrase that you'll see very frequently when people are talking about document databases or MongoDB or NoSQL is scaling out. And scaling out means that what is the best way to deal with things when you get more data? More and more and more data keeps pouring in, as it does, and you still have to sort of store it and deal with it. Okay, well, the simplest way to deal with more data is to just add more computers, to have more servers serving your queries. Okay, so you've got a computer with a disk, you've got another computer with another disk. More data comes along, you just buy another one. Okay, that's called scaling out, or sometimes it's called scaling horizontally, and that's sort of okay with a document database because you can just pile a whole set of complete documents into your first server, another set of complete documents into your second one, another set of complete documents into your third one, and then there's sort of not much communication between the servers, so all you really need to do is locate the server that contains the document and then query the document. So scaling out is cheap and easy and sorted and suited to a document database. If the server has the right document, then it can just answer the query. If it doesn't have the right document, it can't do anything, but it can decide that very quickly. In SQL, it's much harder to scale out because the format in which the data is organized, in other words, tables, is not really the format in which the data is used, which is largely finding out information about a particular entity. So if you've got if you're trying to scale out and you're putting some tables on one server and some tables on another server, well then that's going to be difficult. But then you can't really split tables very easily between servers. You can't have like a little bit of student in this first server and a little bit of student in the second server, because you never know which rows in which tables are going to need to refer to each other. So for a relational database, you don't really have, I mean, scaling out is not is much more difficult to do. And so the temptation then is, instead of scaling out, is to scale up, which refers to replacing your small machine with a bigger machine. But scaling up is expensive. Scaling out is cheap because you can just buy the same size existing hardware and just replicate it. It just costs twice as much as you originally paid. Scaling up, on the other hand, is you run into limitations. as you buy machines with a very large amount of RAM, to buy another machine with twice the RAM is much more than twice the cost. I mean, like, you can probably buy a computer with 1 terabyte of RAM, but getting one with 2 terabytes is going to be much, much harder. So, MongoDB, everything's in one place. The entire information about an entity is just located in one document. The price you pay is there's repetition. If you've got, if you are referring to the same actor in multiple documents, then if you store them in their as a full document, well, then that actor is then repeated for every movie that they appear in. So, and so you have redundancy and you have increased storage, but you sort of have, in some sense, some conceptual simplicity in that everything about the entity is stored in one location. Okay, no doubt in your future database careers, you will be using document databases as well as SQL, and so it's all a question of using the right tool for the right job.